Okay, so in previous lecture we were doing first shifting theorem, and we did the first shifting theorem, and we tried to. I gave you two questions. That is, I wanted you to find Laplace transform of e to power 18 to cos pt. What one needs to see is that what is the Laplace transform of cos pt? So Laplace transform of cos pt is simply, I think it is s upon s square plus p square. And if you replace this, if you multiply this with e to power 18, so I've told you if your function's Laplace transform ft's is capital Fs, then the Laplace transform of e to power 80 ft is simply uh, written as instead of s you will write s minus a. So Laplace transform of e to power 80 cos pt is simply s minus a ka whole square, and then you have p square. Similarly, if you want to find Laplace transform of t to power n, then you know that your Laplace transform of t to power n is simply n factorial divided by s to power of n plus 1, n factorial upon s to power n plus 1. And now if I say that, okay, you have to find the Laplace transform of e to power 80 into t to power n, then it would be equals to what? It would be equals to n f of s minus a. So this would be n factorial divided by s minus a raised to power n plus 1. So this is what it is. I think this is quite clear. Now, let us focus our attention to second shifting theorem. Let us see if people are. Let me wait for people to join in. Okay, so just give me a minute or two, and then I'll start with this. This is second shifting theorem. So before I start the second shifting theorem, I will introduce to you a function called as unit step function in the literature, or in literature at times it is referred to as Heaviside function also. It is also referred to as Heaviside function. So how to define it? You can also write at UA x, then it also means the same thing. I will use the notation h x minus a. So h of x minus a, it is equals to 1 if x is greater than a, and it is equal to 0 if x is less than. This is called as unit step function, or Heaviside's unit step function, or whatever. Like at times it can also be written as Heaviside's function. So how would the graph would look like? So I can write if a is greater than 0, if a is greater than 0, then I can make the graph in this fashion. So for all a less than 0, your function is 0. And for all a greater than 0, your function is simply 1. So this is how your unit step function look like. So for all x greater than 0, for all x greater than a, your function will assume a unity, and for all x less than a, your function will be 0. So here you can see that here. Okay. So it is discontinuous. Clearly, this particular function is for all x equals to. Okay. So let me wait for people to join. Let's start. Okay. So let us see how many people are joining. But right now, I have defined this particular function. This is called as unit step function or Heaviside unit step function. I want to find what would be the Laplace transform of this. And this is all what I'm doing before my second shifting theorem. So before second shifting theorem, let me find the Laplace transform of Heaviside function. Okay. Now there may arise two cases. Because see, whenever you are trying to find Laplace transform, this will be e की power, let's say, because the independent variable here is x, so I'll use x here. Okay, now if a is less than 0, if a is less than 0, let's say this is your a, then for all x greater than a, your Heaviside function would be 1. Okay, so I think Alpna is right. So let me reiterate whatever I was telling. So I was teaching unit step function, and this is sometimes referred in literature as Heaviside function. Okay. So if I write h of x minus a, or this notation also, that is u subscript ax, what does it represent? It represents 1. It is equals to 1 if x is greater than a, and it is equals to 0 if x is less than a. This is 1. Now I'm interested in finding the Laplace transform of this particular Heaviside function, or you can say unit step function. Now, what would be the Laplace transform of h of x minus a? I can write it as 0 to infinity instead of t. Now the independent variable is x, so just don't get confused. Here I have written t instead of x. Sorry, here I have written x instead of t. So e की power minus s x h of x minus a dx. Now there may arise two cases. One case can be if a is less than 0. So if a is less than 0, so I have picturized it in this fashion. Let's say here is your a. Now for all x greater than a, your Heaviside function would be 1 over. So for all, so here I can say that my Heaviside function, this is clear. This is one thing that one needs to see. Understandable. ये चीज समझ में आई नहीं है. कहाँ चले गए? Alpna, is that clear or not clear? See, अगर a less than 0 लोगे, तो a तो ही रह गया आपका. For all x greater than a, your function would be 1, and for all x less than a, your function would be 0. And for all x greater than a, your Heaviside function would be 1. Is that clear or not clear? इसमें क्या है? समझो जल्दी से फटाफट से. अब देखो, थोड़ा ध्यान से देखो. Okay, is that fine, or should I repeat it again? देखो, what we are doing, we are trying to do second shifting theorem. Point number 1. Before doing second shifting theorem, I am saying, I'm explaining first what is known as a unit step function. Okay, so you write it in this fashion, or you write it in this fashion, one and the same thing, because unit step function in literature you will find at times it is referred to as Heaviside function. Okay, so I have written h of x minus a, and it is equal to 1 if x is greater than a. It is equal to 0 if x is less than a. Here is the graph. Okay, now discontinuous. It is a discontinuous function for all x equal to a. Now let us try to find the Laplace transform of this unit step function. that is h of x minus a. Now, what will happen? There may arise two cases. One, what if a is less than 0 and what if a is greater than 0? If a is less than 0, if a is less than 0, what will happen? If a is less than 0, what will happen? See, if a is less than 0, here is your a on the negative x-axis. And for all x greater than a, your function would be 1. And for all x less than a, your function would be 0. Yes or no? And here, your x is varying from 0 to infinity. Here you can say that your x is varying from 0 to infinity. Now you see that if your x varies from 0 to infinity, your Heaviside function would be 1 only. So what would be the answer to this? From 0 to infinity, this would be e to the power minus sx dx, and this would be simply 1 upon s, because this is simply finding the Laplace transform of 1. So what I can write? I can write that my Laplace transform of h of x minus a, that is Heaviside function centered at x equal to a, would be equal to 1 upon s, provided a is less than 0 or even equal to 0. Because at equal to 0 also, for all x, like if a is equal to 0, again you can see that for all x greater than 0, your Heaviside function would be 1 only. Is that clear or not clear?
Yes, sir.
So for all a less than equal to 0, your Heaviside function's Laplace transform would be 1 upon s. What about, what if a is greater than 0? What if a is greater than 0? Okay, what if a is greater than 0? Sorry. Just give me a minute. Okay. कैसे करूं? एक दो just एक क्या है? ठीक है. So what if a is greater than 0? A is greater than 0 means what? Where your let's say here is your a.
Also
Now
1 by
here it will be 1, and for all these values it will be 0. I'm not bothered about less than 0 values, because Laplace transform after all is evaluated from 0 to infinity only. That is, your x should vary from 0 to infinity. Now here there would be two cases. One case would be to move from 0 to a, right? Where your Heaviside function would be simply 0. And from a to infinity, your Heaviside function would be equals to what? It will be simply equals to 1 here. Is that clear? Here it will be 0, so forget about this. Is that clear or not clear? And so this would be equals to e to the power minus sx divided by minus x from a to infinity. This integral would only exist if s is greater than 0. And only if s is greater than 0, and this would be equals to what? I think this will be equals to e to the power of minus as divided by s. And this is only true if a is also greater than 0. So for all a greater than 0, s greater than 0, this would be the Laplace transform. Is that clear or not clear? Yes or no? फटाफट बोलो बेटा. A से लेकर infinity के बीच में your unit step function would be 1. From 0 to a, your unit step function is 0. So when you will integrate from 0 to infinity, from 0 to a, since it is 0, so it will remain 0. And from a to infinity, since it is 1, so I'm writing it 1 here. Writing 1 here. Is that fine? So what I'll write, that my Laplace transform of h of x minus a is simply equals to 1 upon s, provided a is less than equal to 0. And if a is greater than 0 and also s is greater than 0, then it is equals to e to the power of minus as divided by s. So this is how you define the Laplace transform of your unit step function. Is that clear or not clear? ये चीज समझ में आई कि ऊपर से चलेगी?
yes, sir.
Kalpana, is that clear? So good enough. Now let us see. Now this is one, and then see, एक काम करते हैं चीजें समझने के लिए. Let us start from a very beginning. So I knew that my Laplace transform of e to the power, so Laplace transform of ft was e to the power minus ft minus st ft dt from 0 to infinity. This was my Laplace transform, right? What if I multiply it with e to power minus, let's say, sc? So what I'll get 0 to infinity. Here you get e to power minus s c ना, तो एक काम करते हैं, c plus t ft. So I have multiplied both sides with e to power minus sc. This particular integration is being evaluated on t, so don't worry. You can place this particular inside also. This particular term, e to power minus sc, inside the integral term. Don't worry about it. Is that fine? Now what I would do is, I would try to take a new variable to it, and I'll define, let's say, c plus t as equals to y. So your dt would become dy, and your t would become simply y minus of c. Okay, so this particular integration would then run from where to where? This particular limits are on t. So if your t is 0, then y is equal to c. And if your t is infinity, then it is infinity. Then it is e to power minus sy f of y minus of c, I think dy. Is that clear? Now see, whenever you define your Laplace transform, what you do, you try to you always write the limit from 0 to infinity. You try to write the limit from 0 to infinity. So what I'll do, I'll multiply this particular term with my Heaviside function. I'll multiply this particular term with my Heaviside function. Why? Because from 0 to infinity, 0 to c, there is no such integral here. So what I'll do, I'll do some clever thing here. So I'll write it here. So what I'll do, since I know that Heaviside function on c would be equals to 0 if y is less than c, and it would be equal to 1 if y is greater than c. So what I will do, I will simply try to manipulate with this particular integration. So this particular integration, instead of from going from c to infinity, left hand side I'll write it from 0 to infinity in such a way that the term from 0 to c does not contribute. So what I'll do, I'll simply write it as 0 to infinity e to power minus of sy f of y minus c into Heaviside function x minus. Is that clear or not clear? Is that clear? देखो 0 से लेकर c के बीच में, so from 0 to y, from 0 to c, this will be 0, and from y c to infinity, this would be equal to 1. So from c to infinity e to power minus sy f y minus c, ये तो रह जाएगा. Eventually this particular thing and this particular thing are one and the same. Is that clear?
Yes, sir.
Okay, so on the left hand side, on the right hand side, you can see that this particular thing, that is e to power minus cs fs, is simply from 0 to infinity e to power minus sy, and this is f of y minus c, h of y minus c. That is simply equivalent to taking the Laplace transform of this particular function. So it is like Laplace transform of the product function, and that product function is simply f of y minus c, Heaviside function y minus c. Okay, and this brings us to something called as second shifting theorem. So what does second shifting theorem say? Now you'll be able to understand. What I wanted to explain was second shifting theorem. So what does second shifting theorem has to convey us? That if capital Fs is the Laplace transform of ft, the Laplace transform of f of t minus c, h of t minus c, provided c is greater than 0, is simply e to power minus sx fs, or the inverse, Laplace inverse of f of t, Laplace inverse of e to power minus cx fs is equals to f of t minus c into h of t minus c. Is that clear? So mathematically, this is what you refer to as your second shifting theorem. That is, if your Laplace transform of ft is simply f of s, then Laplace transform of f of t minus c into h of t minus c is simply e की power of minus sx fs. And this is what you refer to as your second shifting theorem. इसी को आप बोलते हो second shifting. Is that clear?
Yes, sir.
Okay, good. Now let us try to do something relevant to some periodic patterns. And right now I'm not writing the entire thing. Like I'll do something for you in the later stages when I'm going to write what is the Laplace transform for a periodic function. Let us try to use these few things that we have developed right now, and let us try to use the definition of unit step function in finding the Laplace transform of the functions of the following functions. Okay, so let us try to find the Laplace transform of. Let us try to find the Laplace transform of the following. And then I will also explain you what is the Laplace transform of a periodic function. But right now, let us do it in the most essentially, you can say, basic manner. Okay, Laplace transform of following periodic inputs, you can say, or functions, you can say. Okay, so I'll make a function, then we'll discuss it. Shapes this. Okay, so this is your okay, so just find these gaps. Okay. Okay. So this is clearly a sort of periodic square wave, and let us take some amplitude as k. So let us take the amplitude as k. So I'm writing k here and minus k. Is that fine? And this is a. This is 2a. This is 3a. This is 4a, and so on and so forth. Is that clear? So this is clearly a square periodic square wave. Of amplitude k. Is that clear? Is that clear? Not clear? Is that clear or not clear?
Yes, sir.
Okay, so we'll see when it comes to periodic functions also the Laplace transform, how we are going to do it in more general fashion. But right now I'm trying to do it using the definition of Heaviside function or unit step function, so that at least you will find some sort of significance of whatever we have done just previously. Okay, and then you'll see that this particular thing would coincide when we are going to do the same thing using Laplace transform of a periodic function. So I'll generalize this result later on, but let us try to do it in a very difficult fashion at first. So you can see that whenever your t lies between 0 and a, your function ft is simply your sorry, k. Here it is k, and here it is fine. From t lying between 2a to a, you can clearly see that your function ft is simply minus of k. Is that clear? How to write it in a fashion that that your function can be expressed in one complete. I want to express my function in a way that I can write this particular function in one complete row. So what I'll do, I'll take the help of Heaviside function. And what I'm going to do, you just see Heaviside function. See how. So what I'm going to do is, let's say this is my function, na? ft is equal to this. So I'll write simply k here, and I'll write minus 2k h of t minus a. And why I have written 2k? Because k में से अगर 2k घटाओगे तो minus क्या आ जाएगा, right? So see, whenever your Heaviside function was less than, whenever your t was less than a and greater than 0, so your Heaviside function for all those values would become 0. So simply k would remain. And whenever your Heaviside function lies from a to 2a, no, whenever your t lies between a and 2a, your Heaviside function would become 1. So it will correspond to minus k. Is that clear? So these two definitions can be expressed in this particular single term. Is that clear or not clear?
Yes, sir.
गुड इनफ. ये चीज समझ में आई आप तक कि नहीं समझ में? देखो, ये दो अलग अलग डेफिनेशंस लिखी हैं, इनको हमने एक डेफिनेशन में सेट कर दिया. कैसे? आपने यूज किया हेविसाइड वेव फंक्शन, हेविसाइड स्टेप यूनिट स्टेप फंक्शन. और देखो यहाँ पे t अगर 0 से a के बीच में रहता है, दैट इज इफ योर t lies between 0 and a, then Heaviside unit step function would correspond to 0. And if your t is greater than a, less than 2a, then your Heaviside unit step function is 1. So k minus 2k is minus k, and if it is from 0 to a, that is if your t lies between 0 to a, your Heaviside unit step function is simply 0. So your ft would remain k minus 0 for the first case, and for the second case, it will give you k minus 2k, that is minus of k. I hope it is clear. Okay. Now, now you know that for your that your ft is simply k for all t lying between 2a to 3a. Is that clear? From 2a to 3a, you can see that your unit step function, your square wave output gives you k. So what I'll do, I'll again do something that will put each of these things into one perspective. This is fine, but then I will write plus 2k h of t minus 2. Why I'm doing it? See, if my t is lying between 0 and a, so this I'm making a line here. You see, if I say that my t lies between 0 and a, this would become 0. This will also become 0, isn't it? Because this is equal to 1 only if t is greater than 2a, and this is equal to 1 only if t is greater than a. So this would be 0, this would be 0, simply k. If your t lies between a and 2a, then this will be k minus 2k, and this is what? It is only 1 if t is greater than 2a. For t less than 2a, this would be 0. So this will give you minus of k. And if t is greater than 2a and less than 3a, then what? This is equal to k minus 2k plus 2k. This gets cancelled and you get a k. Is that fine? Yes or no?
Sir.
So proceeding likewise, what I can write? Likewise, what I can write that there are alternative plus minus apart from this. So what I'll write, my function ft can be expressed as k minus 2k, h of t minus of a, then plus 2k h of t minus of 2a, then minus 2k Heaviside function t minus of 3a, and so on and so forth. Is that clear or not clear? ये चीज समझ में आई? मतलब इस पूरे वेव फॉर्म को जो तुम ऐसे देख रहे हो, इसको अगर तुम्हें मैथमेटिकली रिप्रेजेंट करना हो in terms of unit step function, this is one of the ways in which you can express it. Is that fine? And right now, just a few minutes back, I found what was the Laplace transform of h of t minus a. It was simply 1 upon s if a is less than equal to 0, and if a is greater than 0, then it was, I think, e की power minus as divided by s. Now, I want to find the Laplace transform of this particular function. I want to find the Laplace transform of this particular function. So Laplace transform of simply ft would be equivalent to writing, अच्छा एक linearity property होती है वो मैंने नहीं बताई, but always remember that चलो मैं लिख ही देता हूँ. If I have two functions, so if I have two functions f and g whose Laplace transform exists, then Laplace transform of constant a multiplied with f, constant b multiplied with g is equals to a times Laplace transform of f and a b times Laplace transform of g. This is called as the linearity property. I forgot to tell you, but this is called as your linearity property. Is that clear?
सर
हाँ बेटा बोलो.
सर ये जैसे हमने पहले 0 to a में लिया था तो बाकी सब हमने टर्म 0 कर दी थी, जो आपने रेड से लिखा है इसके यहाँ पे
ये वाला, हाँ,
जीरो।
जीरो टू,
यस
देखो
सर।
0 to 1 लोगे तो 0 to a लोगे तो ये हैवी साइड unit step function would be 0 because it is equal to 1 only if t is greater than a. This is equals to 1 only if t is greater than 2a. But if t lies between 0 and a, this would be 0 and this would be 0. Now, if
ओके
t
सर।
lies between a to 2a, this is fine. This would become 1. But if t lies between a to 2a, this would become 0 because this is only equals to 1 if t is greater than 2a. Here, what is written? It is written t less than 2. So it
ओके
will be,
सर, क्लियर सर।
है ना? तो इस तरीके से तुम क्या कर पाओगे, ये जो चीज मतलब वेव फॉर्म में बनी हुई है, इसको तुम एक पर्टिकुलर एक फंक्शन के फॉर्म में लिख पाओगे. ये मैं समझा पा रहा हूँ, नहीं समझा? इज दैट क्लियर?
यस सर, यस सर, क्लियर।
क्लियर ना? ठीक है, मैं इसको थोड़ा सुंदर कर ही देता हूँ, ये फिर कंफ्यूजन बाद में क्रिएट. तो ये यहाँ पे क्या था? आई थिंक देयर वाज t minus of 2a, here it is k, और ये भी मैं सही कर ही देता हूँ. क्या है ये? ठीक है, so this is, ठीक है. Now you see, okay, now you see, if I want to take the Laplace transform of this particular function, this is equal to finding Laplace transform of k into 1. So k into 1 is k by s. All these terms you can see, these a and 2a, 3a are all on the positive side of t only. So all of these are positive. So my formula would be this. So what I'll do, I'll simply write minus of 2k e की power minus as divided by s, then plus 2k e की power minus 2as divided by s, then minus 2k e की power minus 3as divided by s, and so on and so forth. Is that clear? अगर लैप्लास ट्रांसफॉर्म लोगे तो देखो यहाँ पर क्या है, k का लैप्लास ट्रांसफॉर्म हो जाएगा k by s, इसका लैप्लास ट्रांसफॉर्म क्या होगा, e की पावर माइनस as डिवाइडेड बाय s, इसका लैप्लास ट्रांसफॉर्म होगा e की पावर माइनस 2as डिवाइडेड बाय s, इसका लैप्लास ट्रांसफॉर्म होगा e की पावर माइनस 3as डिवाइडेड बाय s, एंड सो ऑन एंड सो फोर्थ. k सब में लगी रहा है, सो डोंट वरी. So this is Laplace transform of ft equals to k, I'll take common out, s I will take common out. This is 1 minus of e की power minus as plus e की power minus 2as minus e की power minus 3as. Is that clear? और in other words, एक काम चाहो तो इसको 1 को तो भूल जाओ, write 1 as 1 only, and minus e की power minus as. अच्छा, यहाँ से 2 कहाँ चला गया? 2 का फैक्टर भी रहेगा. So I'll take a 2 common here. तो यहाँ पे क्या आएगा, 1 plus e की power minus as minus e की power minus 2as. ठीक है. अब थोड़ा सा ध्यान से देखो, this is an infinite terms in GP. This is infinite terms in GP, and whenever you have an infinite terms in GP, that is a plus ar square dash 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 arn, and n tends to infinity, this sum is equal to a upon 1 minus of r, where mod r is less than 1. So if you do that, what you'll get, the Laplace transform of ft would simply be equals to k by s, and this is 1 minus 2 e की power minus as. This is a upon 1 minus r. What is r? e की power minus नहीं plus हो जाएगा ये, because 1 minus r is what second, like अगर तुम इसको ध्यान से देखोगे तो what it is, I think एक कुछ नेगेटिव का इशू है शायद। अगर मैं यहाँ से नेगेटिव कॉमन लूंगा तो यहाँ एक नेगेटिव आएगा, इधर एक पॉजिटिव। ठीक है, so you can see that your common ratio is negative of e की power minus as. This is something easy to see, you can see on your own.
Yes, sir.
ठीक है, so I'm just using the formula for the infinite term, sum of infinite terms in GP. So Laplace transform of your ft is simply equals to k by s. तो यहाँ पे आई गया, this is 1 minus 2 e की power minus as, और ये हो जाएगा 1 plus, तो यहाँ पे लिखोगे 1 plus e की power minus as divided by 1 plus e की power of s. And simply Laplace transform of your ft is equivalent to writing k by s, and that is 1 minus e की power minus as divided by 1 plus e की power of s. Is that fine? And if you want to solve it further, because the answer in the book is not expressed in this form, so you can take e की power minus as by 2 common out. So this will be e की power plus of as by 2 minus e की power minus as upon 2 divided by e की power of क्या था मेरा, minus as upon 2 plus e की power of minus of as. And eventually you can write this as, I think, a sine hyperbolic upon cos hyperbolic. This is tan hyperbolic. So k by s tan hyperbolic as. Is that clear? So this is, I've solved it in another fashion. Our book says that you have to use the formula for the periodic formula. So I'm not going to use it right now. We are going to use it when I derive it for you. That Laplace transform of periodic functions. Right now, this would be the case. So this Laplace transform of ft is equal to k by s then hyperbolic as. Is that fine?
Yes, sir.
Okay, now let us do one question and then we'll finish off this particular meeting and then we'll meet tomorrow. This how to find the Laplace transform of this function. Let's say this is your 1, this is your 2, this is 3, this is 4, and this is 5. And I'm making a staircase here. Okay, so such a staircase function is given to you. Okay, and what I want from you is to find, and this is 1, this is 2, this is 3 here, this is 4 here. Are you getting my point? This is 5. So I'm not able to make it in a very nicer fashion that I made initially because of the lack of the time. But I'm just showing you different colors that, okay, this is how. So how to write this function? So what I'll do, I'll now, because you know things, so I'll just start with writing that ft would be 1 if t lies between 0 and 1. Okay. Now it is equal to 2 if t lies between 1 and 2. So what I'll do, I'll add 1 into Heaviside function stationed at 1. So see, if t is greater than 1, then this would be 1. So it will become 2. And if t is less than 1, this will only remain 1. Is that fine? देखो यहाँ तक आपको ठीक है. Now see this particular thing. So I'll write again 1 into h of t minus 2. Now you see, if t lies between 0 and 1, this would be 0. This would be 0, simply 1. If t is lying between 1 and 2, this will be 0. This would be 1. This would be 1 plus 1, 2. If t is greater than 2, less than 3, this would be 1, 1, 1. This would be 3. Here it is. Is that clear? And so on and so forth. So what I can do, I can write my function ft as simply 1 plus Laplace, Heaviside function t minus 1, Heaviside function t minus 2, plus Heaviside unit step function t minus 3, and plus h of t minus 4, so on and so forth. Is that clear? I think this is quite clear to you. And if I want to find what would be the Laplace transform of this particular function, so I'll write here Laplace transform of my ft would be simply equals to 1 upon s, then e की power minus s upon s, then plus e की power minus 2s upon s, then e की power minus 3s upon s, And I think this is something that you can do on your own also. Even if you use this, I think इसको ऐसा लिख सकते हो ना तुम, e की पावर -0 ऐसे फॉर्म। ठीक है, तो ये हो जाएगा a वाला टर्म क्या हो जाएगा, 1/s को कॉमन ले लो, दिस इज 1/1 प्लस 1 माइनस e की पावर -s, and it is simply 1/s into 1 minus e की पावर -s. Is that fine? There's still time, so let us do one more question. Try to find the Laplace transform of this function for me. Try to find the Laplace transform of this function ft given by, I think, 2 if t lies between 0 and pi, and if t is otherwise, if you just simply write it as 0, then what would be the Laplace transform? So see, what does it say? That whenever your t lies between 0 and pi, it is equal to 2, and otherwise it is equal to 0. So how I am going to express it? So if t lies between 0 and pi, I have to maintain a 2, and otherwise I have to maintain a 0. So I know that it is equal to 0 if t lies between, it is equal to 2 if it lies between 0 and pi. So one thing is very much sure, that I can use this thing, that if my t lies between 0 and pi, this is equal to 0, and if t is greater than pi, this is equal to simply 2. Is that clear? And I have to somehow express it in this fashion, that for other cases, that is for t greater than pi, it should be 0 also. So what I'll do, I'll simply write 2 minus 2 times of Heaviside function t minus pi. Now you see, if t lies between 0 and pi, this will become 0, and this will remain 2. If t is greater than pi, this will remain what? It will remain as 1. 2 minus 2 is 0. Is that fine?
Yes, sir.
Okay. And now I can simply find my Laplace transform of my ft, which will be simply equal to what? It will be simply equal to 2 by s minus 2 e की power minus pi s divided by s, which is equal to 2 by s 1 minus e की power minus pi s. Is that fine? ये चीज समझ में आ गई?
Yes, sir.
Okay, good enough. तो इस तरीके से you can do these things. एक काम कर सकते हैं, because there is some bit of time left. So what I'll do, I'll try to write one thing, how to find the derivative of the Laplace transform. How to find the derivative of the Laplace transform. So f of s is given by e की power 0 to infinity e की power minus ft e की power minus st ft dt. Now there is something called as parametric derivatives. So whenever your parameter is differentiated, because see, this particular function depends upon t, well, this particular integration depends upon t. So if I differentiate with respect to t, what happens? This particular derivative would manifest itself in form of a partial derivative inside. So this is one thing that one needs to remember. So this is Newton-Leibniz formula for differentiating under integral sign. Like this is this comes in a very you can say that later stages of real analysis. So I'll not be able to explain the genesis of it, but you just remember that if I am differentiating with respect to s, your partial derivative goes inside. So this will be simply minus s integral 0 to infinity. Minus s minus t e की power minus st ft dt. Is that clear? अगर partial differentiate with respect to x करोगे तो यहाँ पे s के साथ कौन term t, and this will be. If you do it 2 times, what will happen? It will be simply 0 to infinity minus t का whole square. Or I can write this will be equals to what? This will be Laplace transform of minus t ft, isn't it? But this will minus t square e की power minus st ft dt. And this will be equivalent to writing Laplace transform of t square into ft. If you do it 3 times, differentiated 3 times with respect to x, it would be minus t ka cube e की power minus ft minus st ft dt. This is equivalent to writing Laplace transform of minus t ka cube ft dt. Is that fine? And if you want to write the nth derivative of it, nth derivative of a Laplace transform, this is equals to Laplace transform of minus 1 raised to power n, and this is inductively you can prove this is equals to minus 1 raised to power n t raised to power n ft. Always remember. Is that clear or not clear? So this
Yes,
is
sir.
Haji, bolo.
Yes, sir. Clear.
So this is the formula for the nth derivative of the Laplace transform fs of function ft. Now, as a homework, try to calculate the Laplace transform of two of these functions that I'm giving. One, Laplace transform of t into cos pt, and try to do Laplace transform of let's say t square e की power t. These are your homework. We'll see, and I'll hope to see you tomorrow. And we'll start with integral first, and then we'll go along and see how to evaluate inverse Laplace transform. So hardly 3 days topic it is, and we'll finish these things in 3 days. Okay? We'll meet tomorrow.
Okay, sir. Thank you.
Bye-bye.